what happens? Of course, AIC provides guidance for design purposes. Now, these values are used for understanding the behavior of these columns. When we say elastic columns, that means the behavior of the column is dominated by buckling. So that means this part is governed by PCR. When we say inelastic columns, that means the behavior of inelastic columns should be dominated by PY. But when you look at the relationship between loading and PY, you understand that it's not exactly like that, right? We said that, in fact, in theory, when we consider an elastic column, that means the loading should be greater than PY. But in practice, did we use PY? We didn't use PY. We use what? We use only half of the PY. And why is that? There are several reasons. The two of them I mentioned in the past. For example, imperfection of the materials, right? And residual stress. All these issues are responsible for the reason why in AIC standards, we did not say when PY is greater than, when PY is less than P, and this will be the case for inelastic columns. We did not say that. We use half of it. But when lambda C equals the square root of 2, that means that is the case that it could be dominated by either PCR or could be dominated by yielding, by considering all other factors I mentioned before, such as residual stress and initial material imperfection. Okay, so this is the link, and this was a suggestion made by one student many years ago. How do we link structural stability to steel design? Okay, and also, let me move on to inelastic columns. I will use the slides to save some time here. Now, everything we talk about about buckling, this basically by assuming that the cross-section does not yield. And how do we know that the cross-section does not yield, or that the cross-section is still within the elastic range? That means when you have a column, again, use Euler's column. This way everything is easier. When you look at the cross-section, and this cross-section, of course, bending and going that way, that means the neutral axis is like this.
Professor, are you writing something? Because we can't see.
Thank you.
Yeah.
Suppose there's a cross-section, and when you look at the neutral axis and also the stress-strain distribution, the stress-strain distribution can be represented like this. And a student asked me the question about what's the distance C, and this distance C is from neutral axis to the outermost fiber, which is the C here. That's the C we use on the last page. Now, what do I mean by elastic column? That means the maximum stress, either it's a compressive or tensile, doesn't matter. Either you take this value or you take this value. In any case, maximum stress should be less than yield stress. This is the condition we call it elastic columns. So when this is true, we call this elastic column. However, in reality, many of the columns actually could be reinforced or strengthened by additional supplementary components, such that when buckling occurs, the column's cross-section already enters the plastic range. Why is that? And it's because this is actually a conceptual question. You know that from structural engineering, from the courses you've taken in structural engineering, suppose we consider a frame structure like this. And you have many different kind of structural components. You have columns here, you have beams, right? You also have slabs, of course. In this configuration, you cannot really see slabs. So suppose you see the slab is right here. So tell me, which ones are more important? You have slabs, you have beams, and you have columns. I don't want to write in particular order, but let's say that slabs, columns, beams. What is the most important structural component in the building? Which one?
Aren't they all?
I'm sorry?
All of them?
Columns.
I think it's the columns.
Why?
Because
I say all of them. All three.
Columns provide a load path to the foundation.
Mm-hmm.
Without columns, you wouldn't be able to build up in the first place.
Mm-hmm. True, true. Now, is there anyone who disagrees here? No one, right? Now, the easy way to explain this is to look at what we call load transmission paths. That means when the structure is designed for taking loads, what is the transmission path for this loading? Suppose you provide this total force, what is defined as W times the entire cross-sectional area, and then you pass to what? When the loading is carried by slabs, and the slab will pass the loading to what? To where? Slab takes load, right? Slabs provide functionality. That's why you are in the house. Just look around. Where are you sitting at? You are standing on a slab because slabs provides functionality. Nobody is standing on columns, right? I truly hope not. So slabs provide functionality. And what does the load that slabs carry pass to?
Beams.
Yes, pass to beams. And what does the beam pass the load to?
Columns.
Columns. That's why columns are very important, because if you have if columns fail, you will not be able to take all the loads. That means the whole structure will lose its functionality. And that's why in the design, we have this concept is called strong column, weak beams. That's the design concept. Therefore, it is possible that even when columns enters the plastic range, that means a part of the column starts yielding, we still do not want the structure to fail. So that's why the plastic theory or the behavior of inelastic columns is also important in structural stability. And there are different theories to predict it, to predict the behavior of inelastic columns. And I would like to start with the few ones. You have this part from my slides, so you can just read them. I'm not gonna project them because this way I will have to go back and forth. So please bear with me by reading your own slides and copy the notes from my notepad. All right. The first theory I like to recall is called tangent modular theory. So in tangent modular theory, the behaviors, I think I still have to go back. That's easier to show you this configuration. In tangent modular theory, we simplified the failure or the yielding of the column by two straight lines. And the consequences for that is when it comes to calculating the plastic loads, we're gonna have this kind of behavior. Okay. That is I have this one here. First, we assume that after the yielding, the plane will still remain straight. And that means the only thing changing here is only the curvature. And we assume that this curvature change follows a linear pattern. So when we look at the stress-strain relationship in tangent modulus theory, the stress-strain relationship is like this. We assume that start with a straight line. And after yielding, it will be reduced to another straight line, which means that the slope after yielding is constant. I mean, the slope on the stress-strain relationship. Before yielding, this is well known as the original Young's modulus. And after yielding, this value here is what we call tangent modulus. Hence the name tangent modulus theory, because of this parameter that we defined. Now, when we applied it, when we put it in use, the increase of the maximum stress after yielding, that means after this point, because when the cross-section reaches the maximum stress, which is starting from here, after entering the inelastic range, the incremental maximum stress can be represented not by the original Young's modulus, but by the reduced tangent modulus, which can be written by delta sigma max equals to ET times delta epsilon max, which is nothing but to say that after yielding, the slope will be reduced from E to ET. And of course, in terms of internal moment can be written by this, by tangent modulus times mass moment of inertia times curvature. And here, let me define the first one. Here, ET is what we call tangent modulus. And curvature here is, you already know, that is the second order derivative of y with respect to x, or you can simply write it as y double prime.